Thanks very much for the introduction. Maybe as a disclaimer in advance, this is about combined complexity stuff and barely touches the surface of circuits. But I guess regarding some discussions from Wednesday, I think it's still could be still very interesting for this. Okay, so I guess we all can agree that like in the last couple of years, there has been significant progress in solving combinatorial hard problems in practice. And one of the frameworks that one could use there, besides, say, satisfiability, is also programming or logical programming, where we model problems by means of logical programs, and solutions to these programs are called answer sets. In fact, it's a quite generic framework used both in academia and industry. So there are already two university spin-offs. One is from University of Calabria, one is from University of Potsdam in Germany. So what we can do there is like model combinatorial hard problems like optimizing shifting plans or assigning machines products in different production phases to machines such that the overall production phase is optimized. We can also do like certain logistics problems, like in a classical warehouse scenario where we essentially have goods that we need to bring from a warehouse to a dispatching system, such that this can be done via, say, robots that kind of transport shelves from one location to the other, such that they do not collide. And we want to do this efficiently. We can also do train scheduling and so on. So what do these problems have in common? Well, they can be modeled as a combinatorial problem. Now the question is why, and like in which cases can we solve them efficiently? Well, actually the answer is not fully settled. So it's still not clear, like whether I give you a SAT instance or a logic program, and ask you, can this be solved efficiently in general? What we know though is that like the instance structure might help. And this is exactly what this talk will be about. So it's about treewidth, one of the most cited combinatorial invariants. So like in general, we know that problems on graphs or like arbitrary structures are quite hard. But if we look at the special cases, like bounded treewidth, then most of problems become easy, or many of them become easy. And treewidth is usually defined in terms of tree decompositions. And the tree decomposition can then be used to obtain so-called FPT results. So we are focusing on algorithms that run in time polynomial and instance size. But additionally, the runtime also depends on the value of a function, depending only on the parameter treewidth k. So in a sense, we want to restrict the hardness or the combinatorial explosion to this treewidth parameter, which is in contrast to the general case where we cannot confine hardness, right, a priori. So the question now is, how do these f of k look like? And if we have specific f of k's, maybe can we do better? Can we improve? So kind of as an intuition, these f of k's give you so typically the way these algorithms work is like one does dynamic programming on the tree decomposition where we essentially compute for each node a table. And then in the end, we need to like modify these tables from the leaves towards the root. So it's a bottom-up computation. And when we arrive at the root of the decomposition node and there is a non-empty table, we know there is a solution. We can actually construct these solutions. So this f of k kind of gives how hard or what we expect in terms of runtime for each of these tables, kind of the sub-problem solving effort. And treewidth kind of gives you like the largest sub-problems that we encounter kind of during these computations. So how do these functions look like, and can we do significantly better? And then maybe as a side question, does this imply consequences in practice, or like depending on different f of k's, do we still expect solvability in practice? So what I will show in the next couple of minutes is a decomposition-guided reduction, which is a parameterized reduction that gets a tree decomposition. For now, we can just assume a polynomial-time reduction. And the purpose of this reduction is, given an instance and the corresponding tree decomposition, reduce to another problem such that we immediately get a tree decomposition of the resulting instance. So it's kind of a polynomial-time reduction, if you want, for this talk, where the instance we construct via the reduction has a tight relation to the tree decomposition where we started from, like a functional dependency. With these reductions, we can show specific runtime upper bounds for several problems relevant to AI and knowledge representation and reasoning. Here we'll mainly focus on specific f of k values for logic programming. We accompany this by corresponding lower bounds under the exponential time hypothesis, where we provide a brief glimpse into how one can show lower bounds for problems harder than the polynomial hierarchy when they want to use treewidth under the exponential time hypothesis. And finally, we still show how, despite certain, say, scary f of k functions, we can still efficiently utilize treewidth to some extent in practice. So what we can do is we can do a table, right? Specific decision problems. We can also do counting problems there, non-classical complexity results, and corresponding random dependency. What might be interesting here is like the difference between tight ASP and normal ASP. These are specific fragments of logic programming. Both are NP complete, but the treewidth dependency is expected to be different under the exponential time hypothesis. So for normal ASP, we're expected to require slightly more effort, despite both have the same classical complexity. Yeah, and then there are different extensions of logic programming and harder fragments that give you larger treewidth dependency. Okay, so back to treewidth. I guess most should be familiar now with treewidth since this appeared already several times in the course of this workshop. So treewidth kind of gives a way to capture the tree-likeness of a given graph, or essentially shows how close a certain graph is to being a tree. So what is a tree decomposition or joint tree? We also had this read several times. So a tree decomposition of a graph is just an arrangement of the graph into a tree, where each node of the tree called back gets assigned vertices of the graph, such that we fulfill three properties. All the vertices of the graph for which we compute the tree decomposition have to be captured by a tree, so they have to appear at least one back. Every edge has to be covered, so two endpoints of vertex are covered. Every edge has to be covered, so the two endpoints of each edge have to appear to get at least one back. And finally, connectedness is important for us to design nice algorithms on top. So if you restrict the tree to a certain vertex, the result is to be still connected, which you can check here for all the vertices. Most importantly, the width of a tree decomposition is the largest back size. And finally, the tree width is kind of the best width we can hope for. So like the smallest width among potential tree decompositions. Which in a sense kind of tells us if we want to use tree width, this is kind of the largest subproblem size we expect when we solve the problem. Any questions so far?
What's the complexity of finding the optimal tree decomposition?
You can do this in, it's NP hard, but you can do this in single exponential time in the width. There are like two approximations. I think it's going to be best one in 2 to the k time. Yeah, you can also compute it optimally into the k squared or something is the latest result from this year or something, I guess. Yeah. So, but usually, I mean, if you are just interested in working with a tree decomposition, you can use efficient heuristics. Okay. So what's a decomposition-guided reduction? We have been given a tree decomposition of a graph representation of an instance, and we want to compute a destination instance or an instance of the target problem. And the idea kind of is that we use this decomposition to construct the resulting instance. And then one can do a functional dependency between source corresponding source back and destination back. So in the end, we immediately get the tree decomposition as a result, which functionally depends on the instance, on the tree decomposition of the instance, which allows you to immediately show certain width increases or decreases. Yes, and this was exactly the question that was already asked some seconds ago. Thanks very much. So we can heuristically compute tree decompositions, and we can also approximate them in single exponential time. Okay, so how do we use these decomposition-guided reductions to show upper bounds? Well, the known reductions before from ASP to SAT. Why do we want to reduce to SAT? Well, for SAT, we know that it can be solved in single exponential time in the tree. For ASP, assuming if nothing is known, we want to show this result, right? So the known reductions before essentially didn't quite take care of the tree width. So, and one can show examples that all of these reductions essentially massively blow up the tree width in the worst case, saying instance size large. So what we want to do is we want to do a reduction from ASP to SAT, thereby just slightly increasing the tree width. So from K to K log K in general. Before I'm going to do this, let's briefly revisit answer set programming. So a logic program or an answer set program is a set of rules, which are essentially just implications of this form, where we say we have a positive body and a negative body of each rule. And essentially, this means that whenever we set the positive body to true, all the atoms there, and none of the negative body, then also the head has to be set to true. So this is the one thing, the one side of the semantics. So we require satisfiability in the sense of an implication. But in addition, we require something else. We require that everything we set to true, or everything that we have in our model, is proven. So what does this mean? We require that exists a rule for every such A with A in the head, such that all the positive body atoms are in M and none of these negative body atoms are in M. Actually, there's a little bit more to it. So we should also exclude cyclic proofs, because the idea of this formalism is essentially that you require witness for everything you derive or set to true. So if you have like a cyclic proof that just depends on itself, you, again, just don't have a witness, right? You require everything you derive, that you have a justification for everything you derive. And I think this is one of the simplest formalizations of ASP. Decision complexity is NP-complete, since we can do SAT. I mean, already as part of SAT, satisfiability. Okay, so how do we do this now? Let's look at briefly at an example. Consider the program pi where we have like not B. So we require A if we have not B. We require B if we have not A. We require B if we have A and C, not C. And we require C if we have not D. There are two answer sets of this program. One would be AC and the other one would be BC. Essentially, this can be seen as kind of a guess between, or a choice between A and B. This one is never applicable because here we require that if D is set to false, then C is set to false. So this one is essentially irrelevant. So essentially, we just have a guess between A and B, and we require to have C if we do not have D. Or in other words, all of these are justified because A is justified by this rule, C is justified by that rule, and in this case, B is justified by this rule, and C is justified by the last rule as well. So these are all the answer sets. And in order to utilize tree width, what we need to do, we need a certain graph representation. Here, let's say we are satisfied with the primal graph, where we have as vertices the atoms of the program, and we place an edge between two atoms whenever the corresponding, between two vertices, whenever the corresponding atoms appear together in at least one rule. So this would be like a structural representation of this program. And now, in order to do a decomposition-guided reduction, we need a tree decomposition. We can approximate it efficiently. And the goal would be to kind of guide our reduction along this tree decomposition from the bottoms to the leaves. in order to get a new tree decomposition where we have sort of provability of an atom up to a certain node. So essentially, we have like a linear blow up in the bag size if you compare predecessor bag compared to the successor bag. Okay, so how do we do this? We guide provability for atoms along the tree decomposition. What we can do is, first of all, we check whether all the rules are satisfied. This is just the implication part. So for each rule, using only atoms of a bag, we just essentially write down the implication as a logical formula. Then what we need to do is we need to define provability of an atom up to node T, which means whenever there's a rule in a bag containing X in the head, then either we have provability in this node, which is if there is in the rule we have all the positive body atoms and none of the negative body atoms, or we have provability already below a node in T. And we do this for all the elements of the bag. And finally, we just have to say, whenever we set something to true, so whenever there are something, we require that it's proven in the end. And what do we mean by in the end? Whenever we have a bag with X in it, where it doesn't occur anymore from there on. So this is actually all that's needed. One can easily transform this into a parsimonious reduction by replacing implications here by equivalences. So how does this look on our example? We take the program and corresponding tree decomposition. We construct the formula as specified, essentially just transforming the implications into CNF, which is trivial, right? Defining provability of an atom up to a certain node. And in the end, enforcing whenever we set an atom to true, then we require that it's proven up to the last node. So here, like in T2, A is forgotten because here it appears for the very last time. So whenever we set A to true, we require provability of A up to T2. And we almost immediately get the corresponding tree decomposition with nice properties. So here we see it's linear, and I promised something like K log K, right? The point is this was just for tight programs because I didn't consider cycles so far. What I mean by cycles, as already mentioned, we do not allow cyclic dependencies, positive cyclic dependencies for a proof. So this would be in that case. Okay, so in order to address this, let's just assume such a program where we have cyclic dependency among the positive body atoms. Essentially, we cannot prove any of these atoms because essentially we cannot start, right? The proof of A the proof of B depends on the proof of A, which depends on the proof of C, and so on. So it's this program only has an empty answer set as a solution. So in order to treat these cycles, and this is essentially what gives this blow-up, what we need to do is we need to kind of partially order atoms. So in each bag, we locally order the atoms and ensure that this local ordering is essentially consistent with neighboring tree decomposition nodes. So we require like log k additional bits for each tree decomposition node and guide this information along the tree decomposition. If one carries this out carefully, we obtain the mentioned result. However, the reduction is not parsimonious because essentially we have like a partial ordering, and we do not know global position in this ordering. So the current suspicion is that counting normal answer sets for normal programs is expected to be harder than the decision problem. However, there is no formal proof for it, so I'd be happy if somebody would be interested in that part. So we also did some practical experiments. So we implemented reasoning over logical programs. We also considered the problog, say, formalism. And interestingly, what we compared just like the regular way of encoding provability with provability guided along a tree decomposition. And these N versions are the vanilla versions without using treewidth or tree decomposition. And the other variants are essentially extensions where we use different variants of these decomposition-guided reductions. So it seems that even these knowledge compilers in our setting seems benefit from the information of the tree decomposition. So this is just as a takeaway from this slide. Yeah, so with this, we can also do some other special fragments where we essentially kind of bound, say, the cyclic dependency of positive cycles in the dependency graph of a program. So the question now is, like, can we significantly improve, or can we do better than in time due to the k log k times poly in n? And so, like, can we solve significantly better in time significantly better? And the answer is, unfortunately, we can't, or at least it's very unlikely. So this brings us to decomposition-guided reductions for using lower bounds. So what's known is that, like, the cyclic dependencies are kind of the reason for hardness of logic programs. So there is a known result. So if you do not use additional auxiliary variables, you cannot translate normal ASP to SAT without an exponential blowup. However, this really uses Probabilistic auxiliary variables. So for treewidth, it's actually slightly different. So the underlying reason for hardness, in a sense, is that we do not see these positive cycles in the worst case. So it's like they might be completely spread across the whole tree decomposition. It's similar to, like, following a magnifier glass along a very large cycle or many cycles. So we do not see the cyclic information all at once. So this kind of prevents an algorithm from analyzing the cyclic dependencies. And one can show hardness or the k log k lower bound by reducing from a problem called disjoint paths, where we want to find vertex disjoint path between pairs of source and destination vertices. And the idea is that, well, we know a bound from this case, so cannot do better than with f of k to the k log k. And the challenge now is to reduce from disjoint path problem with just a linear tree width increase. And again, we can use a decomposition-guided reduction for that and ensure that the tree width increase or the width increase is actually just linear. And the idea is there to do reachability with reachability vertices, but not for each pair, because this would already blow up the width probably, to guide along the decomposition whether you already have chosen for a specific vertex an edge, an outgoing edge. And in the end, we need to link those pairs together in a certain order. Since the order is not clear in advance, we also do this along the tree decomposition, because there we know that this order that has been captured in the tree decomposition doesn't blow up the tree width. Okay. So with that, we obtain the corresponding lower bound. And now the question would be, can we maybe generalize this technique, or can we use decomposition-guided reductions as kind of a tool to show lower bounds for higher level problems? Since in AI and KR, they appear naturally there. And the obvious candidate, or one obvious candidate, is deciding the validity of a quantified Boolean formula, because there we know an algorithm which runs in alpha exponential time in the tree width with tree width on the top. So it's 2 to the 2, height L, tree width on the top. And what we showed is that you cannot significantly improve that on the exponential time hypothesis. And the proof goes by a decomposition-guided reduction from quantified Boolean, deciding validity of a quantified Boolean formula with L quantified blocks to increasing the quantified block by 1. Thus, this increase of quantified block allows you to significantly compress the tree width. So we can compress the tree width from k to log k at the cost of an additional quantified block. And the reductions that have been done so far before were like reducing from 3-set using ETH. So under ETH, you cannot expect, or ETH implies that you cannot solve 3-set in time better than single exponential in the number of variables. The previous attempts were reducing from 3-set to, like, say, QZ2. But the new tree width is like logarithmic in the number of variables of the instance we're starting from. This approach is slightly different. We reduce from k, from 3-set with tree width k to QZ2 with tree width log k. So we have like a relation here. And why is this more beneficial? Well, I would just say it's simpler because with the same technique, with the same idea, we can just reduce from Q sub L to Q sub L plus 1, and essentially doing the same reduction. Whereas I have honestly no idea how to reduce 3 sub with treewidth K to Q sub 3, so 3 quantifier blocks, and making a log n. This idea essentially doesn't easily generalize to that one. So the advantage here is that we can actually do induction over it and obtain a lower bound for other cases. So maybe so I did a weird figure just to show, maybe as a disclaimer, this is kind of a simplified illustration of how the reduction goes. And essentially the idea is as follows. We start with the tree decomposition. With log K treewidth, we cannot, in a bag, refer to more than one element of the original bag. So we use concept of pointers, where we just refer to one element of the original bag. And in the end, these pointers allow us to kind of make a new reduction that gets rid of connectedness of the treewidth. So whenever we introduce a certain vertex of the graph, so we haven't seen it so far in the tree decomposition, we make a new copy. So we have all these copies. And so essentially we don't have connectedness anymore, right? And we can make sure that there is only like a constant number of introducers in each tree decomposition node. So these are like constantly many. And then with these pointers and the additional quantifier block, we kind of repair connectedness again. So it's like, first of all, we destroy the tree decomposition property. So getting rid of connectedness, adding copies. And then using this additional quantifier block, we enable to synchronize these copies such that in the end, the copies are in line as before. So it consists of 3 parts. The guess part is the thing that happens when we introduce the variable. Propagate part happens between neighboring bags, ensuring basically that we repair connectedness. And the check parts ensure that we can actually check corresponding clauses or 3 CNF clauses. Okay. If we still have time, I can show a brief example, which actually doesn't use clauses, but terms. So we have like exists for all QBF with these 4 terms. As before, we can do a primal graph representation. So this would be a primal graph. In order to make it simpler, we can construct a tree decomposition, say again via the 2 approximation. And we construct a tree decomposition where we only have like we only see one term in each node. This just makes it simpler. And then the resulting reduction kind of looks like this. So we have these copies. So if you compare one block from our source instance and destination instance, we have these copies. For the universal ones, of course, when we do copies, we need to shift it to the next existential block because in the end, we want to ensure that these copies have the same value, right? So you cannot just universally quantify both copies. We have the bit variables to ensure that these pointers are in line, right? So that we repair connectedness. And a pointer also has values. So it's like you can point to a certain element of the original bag, and the target also has a specific value, right? True or false. So how does this look like the guess part? It's quite simple, actually. So whenever WT1 is true and we point to W in T1, then also the value of T1, the pointer for T1 has to be true. Same thing for the false case and same thing for the other copies. So this is actually quite simple. The propagate part is not much harder, essentially ensuring for neighboring tree decomposition bags that we can synchronize those. So whenever the value in T4 is set to true, and we point to W in T4, and we also point to W in T3, then also the value for T3 has to be set to true. Same thing for the negative case, right? The check part is a bit more involved. For checking a 3DNF, we need 3 pointers for each of the terms, right? For each of the elements of the term. And we also need to slightly adapt propagation there. And we also need to pass the information of whether we already satisfied this formula along the tree decomposition, which is just constant overhead. Yeah. So in the end, it looks something like this. Basically, this thing just copied 3 times and some satisfiability selection. In the end, we can show that like the treewidth is logarithmic. So we need something like 12 log plus 13. This is just because of technicalities, I guess. Would be interesting on whether we can do significantly better there. Just get rid of this. Just use 3 times whatever. It's because of the synchronization between neighboring bags. Yeah, it's just a linear blow up in the log. In the end, we can show the lower bound by just using induction. Just use the reduction from SAT. Just apply it as long as you need to get there. It's quite simple. It also works for planar structures, so like Q-planar SAT. One can show with these decomposition-guided reductions by using just very restricted decompositions that it also works for bandwidth and cut width parameters. Recently, we extended to feedback vertex size and tree depth. But for the incidence graph, there is a small, say, maybe not so nice thing for the primal graph. We require a really long clause when we generalize this technique. So it would be also interesting to fix this missing case for the primal graph. Any questions so far? So the nice thing now is that we can just use the result, right? So instead of reducing from 3 sub for treewidth k and showing a lower bound for a problem that's expected to be slightly higher in this f of k, say 2 or 3-fold, we don't need to make a new parameter that's like log or something in n, but we can just reduce from q sub l to have a problem. Yeah, of course, depending on what this reduction does, it might change the treewidth, but you don't need to overcome exponential barriers, so to say, all the time. We can do this for different problems in AI and KR, classify according to hardness for treewidth. Maybe to give a bit of like a summary here. So just to kind of visualize decomposition-guided reductions. So if you take the treewidth on the x-axis or largest subproblem size and like largest subproblem size here, kind of, and like subproblem solving effort or f of k on the y-axis, then what these decomposition-guided reductions allow is to kind of go from one spot here. So kind of decrease the subproblem solving effort at a cost of an increase in largest subproblem size, and the other way around, which we did for treewidth. So go to harder fragment that has like smaller subproblems, like from k to log k, as we've seen for the QBF reduction. Still have some minutes, or don't I?
Maybe a few.
Then maybe to like summarize this or to ask the question of what do we do with these classification results? Can we still utilize them in practice? The thing is, we can use treewidth, but what we observed is that kind of an abstract version of treewidth would be ideal. So pick a subset of the vertices of your graph and take the induced subgraph, and then we add additional edges to this graph. Namely, whenever vertices in the set are connected to the same connected component of the graph, of the induced subgraph without S. So this kind of ensures that we see larger subproblems later in one bag of the tree decomposition of the resulting graph. So in other words, what we're doing is we're doing like the simplified graph representation where we can easily do dynamic programming along, but each bag is large. So we have like larger subproblems in each bag, but we do not use dynamic programming on these larger instances. But we use, say, a SAT solver, say, any other existing solver. And we call this concept nested dynamic programming, since you can actually apply this decomposition abstraction phase, decomposition phase in a nested way, and then use other solvers, maybe circuits, actually knowledge compilers, for these large subproblems, say. And this is a system called NestHGP, which works quite well for counting. So what we did is we tested a series of counting instances, so counting the numbers of assignments of a position formula, and projected counting, which is expected to be double exponential in the truth. We did, I would say, reasonable limits on the wall clock time and main memory. And to show some results, what's quite interesting here is that we use sharp sortier as a subsolver. So these are called cactus plots. Maybe just don't go into details here, but like being lower and more towards the right is better, solves more instances faster. So we use this one as a subsolver in order to arrive kind of here. So it's kind of a hybrid tree-width based solver by combining ideas from round-robin complexity and other techniques from model counting. What's quite interesting is that the widths that we work with are really large, like 200 something, just because like we do not materialize solutions. And we just have like a combination of classical CDCL-based techniques with truth-based approaches. And it also works for projected counting. There we also have like there we have a benefit if we parallelize. So this is like the parallelized version. This is the single core version. We see it's kind of competitive, right? It's a bit of more effort, I guess, also because of computing the abstractions and stuff, but it's kind of competitive with what has been up there. And the interesting part is like we still use kind of large decompositions for it being double exponential. This works for many other frameworks and extensions. It's kind of a generalized principle. And just to note, there are also other hybrid approaches available. So to conclude, we have seen decomposition-guided reductions, the application for upper and lower bounds. We showed that ASP might be actually harder than SAT if you believe in the exponential time hypothesis at least. Provided kind of an idea on a lower bound methodology based on quantified Boolean formulas. Currently, we're focusing on non-ground ASP. Yeah, there is the interesting circumstance that you can actually simplify queries kind of, just because the formalism is already quite high on the second level of polynomial hierarchy, which allows you to simplify queries such that can essentially, we do not need to evaluate the whole body of a rule as once, but we can actually split the bodies. What's still open is the result for sharp ASP, the lower bound. I still expect that it's double exponential, to be honest, and I can give some arguments about that. One can still think about lower bounds for other parameters, and I mean the concept is quite general, right? And it would be quite nice to have theoretical models for using high tree width in practice, because obviously high tree width might not be too bad in practice. Just depends on how you use it and how the specific tree decomposition looks like. Thanks very much for attention.
We have one question.
I think it was in the table that you show without the complexity, also the disjunctive fragment of ASP. Does disjunction add any complexity? Can you do the same things if you have disjunction in the heads?
What do you mean the same things? Disjunctive ASP is harder.
Right. I mean, your reductions with the bounded tree width, would they work if you have disjunctions?
Yeah. Why wouldn't it work?
I don't know. I'm asking that.
It's really just a general principle. You just do the reduction guided along the lines of the tree decomposition.
Right. Okay.
And in fact, you can do a reduction from 2QBF to disjunctive ASP, but you take care that you do not mess up the truth in the process.
Right.
So it's really kind of a generic principle, I would say. Okay. Yeah. Thanks for the question.
Right. Thanks, Markus, again.
Thanks.